Go. 3, 2, 1. Hello and welcome back to Calculus2. The lecture of the day for the second time is 9.2, Properties of Power Series. Let's hope that the network holds so we can finish this. What I did is I talked about, so far as I talked about the continuous world, which you grew up with. You learned about numbers, then you learned how to compute with numbers, then you learned about the variables through algebra and equations and right, so on. And then you learned about functions in pre-calculus, and then you finally reached the calculus. So now sequences and all of this create a parallel track where you learn about basic numbers, which would be the sequence. That's the ordered list of numbers. And then when you add all of those, which means you're performing calculations, you're adding all the numbers, that will be series. And then you are introducing x as the algebraic part. You are getting power series, which are actually functions, because they have formula with x in them. And then we learned the properties of that in 9.2, which will allow us to, since now we have functions, do the calculus of power series for power series in 9.4. So I want to consider and analyze the summation of x to the n from 0 to infinity, which we know will expand into x to the 0 plus x to the 1 plus x squared, and so on to infinity. So my question to you was, if I want to consider the convergence or divergence of this power series, when you're looking at this, does it remind you of something that you learned from series? And your answer is? Yes? Yes? What is it? Sequence. Which one? Series. Geometric series. So we have a r to the k from 0 to infinity. Now, actually, I'm going to use n to compare them. Now, this a is 1, so I'm just going to ignore that. Actually, erase it. And now they look the same, right? Except I am allowed to plug in anything for this x, right? So what did we learn? If r is between a negative or no equal, if r is between negative 1 and 1, we have convergence. If r is outside of that range, it diverges. This propagates to the power series right away because that x is actually r. So I look at the power series x to the n, and I say if x is between negative 1 and 1, it converges. If x is bigger than 1 or less than negative 1, it diverges. Now, that's a huge implication because now, guys, you have a function, and by adjusting x, you have the power series to converge or power series to diverge. So now we see that the convergence, and I'm going to write this in blood, all right? Convergence of power series depends on the type of the series as well as the value of x. And I'm going to actually underline that part. The convergence or divergence depended earlier, right, in chapter 8, depended on, you do the test, and you have those rules for convergence and divergence. So if you're geometric series, you know what to look for. If it's telescoping, you know the procedure. If it's integral test, you do prove those three things and you do the integral test. So the convergence or divergence dependent on what kind of formula you have there. Now it's the type of the formula and value of x in addition. So we are going to talk about the basic properties of these, and those would be the properties of interval and radius of convergence. We need convergent series. Convergent series provide us with the output. Divergent series provide us only with explosions. That's all they provide. Because remember what the series is. It's a sum. So if you're talking about energy and the energy is summing up to infinity, that means that's the explosion, right? So for engineering of any type, you are primarily looking for convergent series. You want, if you're working with signals, you want convergent series. If you're working on a compression in computer science, you want the convergence. You want the convergence everywhere. But you see that, for instance, this particular power series has a very narrow interval on which it converges. This power series will converge if x takes values from -1 to +1, and it will explode for all other values of x. So what we have to do is we have to be very mindful of these kind of things as engineering when you're building something, and we need to know what are the parameters that you could use to, I don't know, the amount of fuel that you need to add, the amount of whatever you're designing. So now, looking at the power series, we are going to consider, and I'm actually now going to consider the three that I actually gave us in the textbook in the section, because those three are absolutely amazing examples. So they picked the best examples possible and did them. So this is one of those very rare things when I do actually the examples that are given in the book. So we are going to consider three power series, and we are going to see how the convergence of those depends on x. So the first one that we are considering is x to the k divided by k factorial from 0 to infinity. So this is the first one. And what I'm looking for, so looking for the interval of convergence. What happened? So I'm looking for interval of convergence. And what I'm going to do here is I'm going to do ratio test. Ratio test is going to be our go-to test for entire 9-2. Very rarely you are going to use root test because it will be easier, all right? But 99% of the time, it's the ratio test. So what am I going to do? Let's do the ratio test. Limit k goes to infinity, absolute value. Now if you drop this, the problem is dead, done. We have x to the k plus 1 over k plus 1 factorial divided by the original problem. And then we just do algebra from there. The second one will be flipped, so this is x times x to the k plus 1. No, to the k, sorry, x to the k. Divided by peel off k plus 1, leave k factorial there. Times, flip the one on the bottom, so k factorial x to the k. These all cancel. And what you get is the limit k goes to infinity of absolute value x over k plus 1. Now, in the eyes of the limit, which operates on k, x is a constant, because the limit is operating on k's. So you are allowed to kick this x outside of the limit and focus your limit-taking skills on 1 over k plus 1 as k goes to infinity.
We still need the absolute value on 1 over k plus 1? Or
No, because k is always positive number. So now what's happening here is, what's the limit of 1 over k plus 1? 0. And absolute x times 0 is 0, which is always less than 1. What does this mean?
that is convergent.
This means that the power series is convergent for all x. So interval of convergence is negative infinity to positive infinity. And the radius of convergence is r equals infinity. By the way, interval of convergence is, in this case, the entire line. Radius of convergence is half of that. Right? You know that the radius is half of diameter, right? If you are confused, why are we talking about the radius and a circle on a flat line? Please remember that this is the introductory. This is still elementary mathematics. So we have something that is called Lorentz series, which are in the complex plane. And if you have the real axis and imaginary axis, and you have a series that does this, it converges on a circle, on a disk. So that's where the radius of convergence is coming from.
Did you show me something like that in Calc 1 when I asked about like some questions 2-5? You showed me some like wacky thing. Infinity isn't infinite. It was like a
No, that was something else.
oh, okay.
So this is the problem. Let's review it one more time. We have a power series, and this power series might converge everywhere, might diverge everywhere, or might converge somewhere and diverge somewhere else for different values of x. So what we've seen here once we did the ratio test is that regardless of what x is, this power series always converges. Moving on to example 2. Summation 0 to infinity of negative 1 to the k x minus 2 to the k divided by 4 to the k. Ratio ready? Great. Limit k goes to infinity. Absolute value. Guys, absolute value is going to kill the negative 1 to the k, right? Because negative 1 to the k is plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. And absolute value is just going to be 1, 1, 1, 1, 1. When you're multiplying by 1, nothing is changing. So we get to ignore the alternating term in the absolute value. We don't need it. So I have x minus 2 to the k plus 1 over 4 to the k plus 1 times the original problem. Flipped. I'm skipping a step. Now we peel off x minus 2 times x minus 2 to the k over 4 times 4 to the k, standard ratio, guys. So please don't invent anything there, just do the standard stuff. Kill, 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 kill. And look what we have. We kick out absolute x minus 2. And we are left with the limit of 1 over 4 as k goes to infinity. What is the limit there? 1/4. So the limit is absolute x minus 2 over 4. Now, in blood, we want convergence. So what I do, I set this less than 1 because I am looking for x values that will give me convergence. So I set this less than 1 because that is in a ratio test condition for convergence. And now I have inequality to solve. Hello, algebra. Multiply both sides by 4. And now what do we do? Exact. We go -4 less than x minus 2 less than 4. Add 2 to all 3 sides. And here's your interval. And what's the radius? How much is the radius? 4.
How can you tell the radius can be 4 because of the less than 4?
How far are these numbers? How far apart?
2, 4. No, they're not 4.
8.
So, 8.
8. You have 6 on one side of 0 and 2 on the other side, so they are 8 units apart. Half of that is 4. Radius is half. So you look at the interval, you see how big is the interval. So you have 6 units to the right and 2 units to the left. So 6 plus 2 is 8. Cut that in half is 4. Radius is 4. Now, we see the interval of convergence, -2 to 6. Observe that there is no less than equal. Remember that the ratio test is inconclusive if it's equal to 1, which is the reason why you set it less than 1 rather than less than equal than 1. Make sense? So now, another thing that I want you to see here, well, we know how to calculate now these things, but do you remember when we did our, when we defined power series, we said if you have x minus a, the series is centered at a. You remember that part?
Yeah.
Where's the center of your interval?
2.
Power series is centered at 2. And your interval. That is your checkpoint on the test. It's not if I put, when I put this question on. You are going to check at the end. Because if I have, let's say, x minus 5, and your interval doesn't have 5 in the middle, you're wrong, right? Because you have to be wrong, right? You have to redo it. Because the series is centered at 2, the power series is centered at 2, your interval of convergence must be centered at 2. And you see that if this is 2, you have 4 units to the left, 2 plus 4 is 6, 2 minus 4 is -2. So radius of convergence, interval of convergence, and the center, they all have to align. If anything is off, problem is wrong, and you have to fix whatever is missing. So I hope you see that. And that's that part. And we have one more example. One more example, which is power series k factorial times x to the k. What can you tell me about this?
Do the ratio.
We're gonna do the ratio, yep. Did you guys notice that you have to have very heavy denominator to get the convergence on series? Because if you have denominator that cancels to 1 over k, in comparison to harmonic series, that diverges. But if you have 1 over k squared, or if you have k to whatever power over k factorial, those kinds converge. If you have not so much increasing numerator, but really massively increasing denominator, that should be, right, convergent. Right? So there's no denominator at all, right? So this screams divergence, right? The whole thing screams divergence.
Divergence test?
Well, no, we're going to use the ratio. Except if x is 0, right? So the whole thing screams divergence because there is no denominator. It can't converge, but it's power series. So 0 and x will make this convergent. But let's do the ratio test and see that. So we have our good old limit, k goes to infinity, absolute value, k plus 1 factorial x to the k plus 1 divided by k factorial x to the k. Limit, peel off. We have k plus 1 k factorial x to the k divided by k factorial x to the k, kill. And look what we got. We got limit, k goes to infinity of k plus 1 times x. This x gets kicked outside. And you have limit of k plus 1 when k goes to infinity. So now, this is 0 times infinity.
How can it be 0 that the absolute value of...
No, x, well, if x is 1, then it's infinity. If x is 10, it's still infinity. The only one that will make this 0 is this. But then you're going to say, wait, hold on. We learned the L'Hopital's rules last class in Calculus 1 that 0 times infinity doesn't necessarily need to be, right? It could diverge. Yeah, but that's when these functions play the role of, if you're thinking about these things, both are linear, both are of the same weight. So it is 0 in this case. So if it's 0, we have convergence at a single point. So in this case, we have convergence for x equals 0 and divergence for negative infinity to 0, excluded, 0 to infinity. Radius of convergence is 0 because it converges at the point. So this power series converges at a single point. Converges only for x equals 0. So you can read the textbook. These are the same exact examples that the textbook gave. And you can read the problems and see, right, another point of view, another explanation. I'm going to challenge you guys now with a homework problem under basic skills to give me the interval of convergence for a problem. So let's start with the vanilla example. Let's say problem 17. So we'll do 2. Summation 1 to infinity x over 3 to the k. This problem?
I did a root test.
Okay.
Wait, you can do the root test for this. And I got and it's k goes to thing of x over 3, but I know you can kick it out the x over 3, but then what do you do with the it would be like 0 then?
It won't be 0, it will be 1.
Be 1?
Yeah. Set. You're looking for convergence, so set it. Less than 1, solve the equation, inequality.
Yeah, that's...
Are we ready? So, limit k goes to infinity. X over 3 to the k plus 1 divided by x over 3 to the k.
Wait, how come you're not doing the root test? I mean,
You can, but ratio test works. So
can you do it both ways?
yep, equals to limit k goes to infinity, and when you peel x over 3 off, you are left with x over 3 to the k over x over 3 to the k. These guys die, and you end up with the limit of absolute value x over 3 when k goes to infinity, which is just x over 3. You set this less than 1, right? Set this less than 1, and then you have x over 3 less than negative 1 less than 1 times 3 everywhere, and we got it. What's the radius?
They proved if it's convergent or divergent, actually.
Radius is 3. What happened, Kevin?
You basically forgot to prove that if it's convergent or divergent.
No, I am setting it equal to 1, so I'm looking for convergence. I'm not proving it. I'm looking for it.
You forgot to do like 0. Come on, your brain hard. 0 times by 1. You forgot to.
What 0 times by 1?
You said equal 0 where you said it is convergent.
No, it's convergent if both root and ratio tests are convergent if they're less than 1.
Okay.
Now, guys, where's the center? Do we see that the center is at 0? Do we see the problem that center is at 0 because it's x minus 0? So everything falls apart, right, in the spot, and we know this is good. Now, if you are using the root test, same problem is done with the root test. Limit k goes to infinity, kth root of x over 3 to the k, and you are just getting x over 3, right?
Yep.
Set less than equal to 1, and you get the same answers. So if you have, k power everywhere, obviously, that might be the faster way to do it. I said, not too many problems would be done that way. Let's see if we can find something. Ooh.
Evil. No doubt. Didn't commit your evil laugh.
No, we gotta save it.
Now,
Oh, maybe you leave it for the test. No, I'm just kidding. That would not be fun, right?
maybe on the final.
Ooh. Wouldn't like to see the evil laugh on the final. So how about? Why not? So this is not evil. It just looks busy. It looks busy. So negative 1 to the k, kx minus 4 to the k, divided by 2 to the k. It's just busy. So you can't use root here because there's that k without kth exponent.
Yep. What you said, pretty much.
Did you get it?
I got it 2 less than k squared minus 3k is less than 6.
What's the radius?
Radius is 6 plus by 2 is 4.
6 plus with 2.
Like it's 6 plus 2 equals 8. Divided by 2 equals 4.
So radius is 4.
Yes.
And the center?
Sorry, radius is 2.
Radius is 2. Radius is 2 and the center is?
4.
4. So as you can see, I immediately peeled off and I flipped the second fraction, and I did everything in the first step to save some virtual paper. All right, no one cares. All right, so the limit is on k plus 1 over k. The rest goes outside, so we have the absolute value of x minus 4 over 2 with the limit of k plus 1 over k, which is 1, right? So we are talking about setting x minus 4 over 2 less than 1. What happened?
Because like basically what I did, I said k plus by 1 and k minus 4, in which I factored everything out and said less than
Yeah,
less
but
than 1.
yeah, but you got it. So whichever way you did it.
No, I meant I forgot to put the x minus 4 on out because I thought it was k minus 4.
Well, somehow you got it then, right?
That's kind of where it won't happen again. I know that's what every teacher says.
Bye.
And Professor, the radius equals 2 because it's divided by 2, right?
Ah, you are picking up the pattern. You are picking up the pattern that the radius of convergence is right here. That the center is right there, and you can just look at the problem and know the solution before. I know.
I feel good about myself now. That's like
That's when you really know what's going on. So next time you out and power series come up,
oh, absolutely. Killing it every time.
and exactly. Well, I mean, if you hang out with right people, it does come up. That's, you know, because I did receive from your friend, right, an email with the receipt from the bar where the integral was worked out. So you're hanging out with with right people.
Exactly.
Not everyone might agree with the diagnosis there, but that's, you know, beside the point. The last segment over here is combining power series.
So I did here, I did a square minus 3k minus 4 less than plus or minus 2 because of the absolute value, and then I got 6 and 2 between the intervals. Yeah, that's the point in which I told you I thought that x minus 4 was k minus 4.
Yeah, it's x minus 4. The last part of this lecture is combining power series. See you next week. Is there a problem? Would you like to state for the world? Combining power series. Did we say that we have equal sign? Oops. We have equal sign in between f of x and the power series. If we have infinitely many terms, we have equal sign there. And I can just go and say another function will have d of k x to the k. Is anyone planning on taking differential equations? Pay attention, all right? Pay double and triple attention right now. Because, remember this?
Yeah.
And we've seen this. If I express this function y double prime as a summation and a function y as a summation, they're added, they're combined together, which means that I will be combining, I will be adding those summations. What follows here is actually algebra that you are learning in Calc2. Your learning in differential equations ended by us telling you you can assume this power series solution. The rest is taking derivatives and combining power series. Has nothing to do with differential equations. It's like you trying to add 3 numbers in Calc 1, right? 5 plus 7 is 12 plus 1 is 13, right? That's that level. So when you are dealing with these things, we are going to now realize that the power series is a function written in a different way, expressed in a different way. So I'm going to express these two functions f and g through whatever their power series are. And now I have a theorem, right, which states, this is theorem 9.4 or whatever, is that power series, so number 1, power series ck plus minus dk x to the k converges to f of x plus minus g of x. This is exactly what we had in differential equations. It was just backwards, right? These things were on the left and these things were on the right. So that's the same thing. So you have to understand these kind of things. The next one is also used. I'm going to flip to differential equations again and show you that piece. Where you have, if you multiply power series this term jumps in, distributes over every term you have, which is infinitely many of them, and you end up with a power series that, just like in algebra, adds the exponents. There are differential equations that you will be solving where this number in front is x squared and so on. And that's actually, let me try to find that real quick. So differential equations, maybe somewhere over here on the bottom. Yeah, there it is. This example. You see how this y double prime is pre-multiplied by x squared? So the theorem you just wrote, your m is 2. And your power series exponent there is n. So when you plug it in later on, it's going to be n plus 2. But then when you shift the counter for the second derivative, it's actually going back to n. So there are a lot of cool things, right? So what you learn now propagates through mathematical plot line for the stuff that's happening later. And the one that we need for this class, number 3, we need this for 9.4, is function composition. Function composition. So what is the function composition? It is when you plug a function into another function. Well, one function is going to be power series now. So what I'm going to do now is I'm going to say that, I can use the same notation that they use, or I could just say there is some kind of age of x that I want to plug in summation of ck x to the n. You know how function composition works. You replace variable x with that function. So what you, yes. So what you're getting is the power series ck age x to the k. I'm mixing n's and k's. That's not good. I'm going to do everything in terms of n. So it's cn. Oh, I have to go everywhere and fix all of these k's into n's now. I mix them up everywhere. Look, ck, and then I have n, and this is the problem. I learned in terms of n. I learned everything in terms of n and used it for a very long time as n and n, and then when we started using this book has everything as k. So I have k's and n's mixed up. It's either all k or all n. So now, why is this important? This last step. This last step is very important because we can create functions with this. From known power series, you can create more complicated power series, which is usually what the problems have. So without going into differentiation and integration, we're going to go into 9.4, which is extremely short, to actually use this there. So this ends 9.2, and the next section will be 9.4. We'll restart everything. So let's go take a quick break, and then when we come back, we'll still have time for the lab after that, I guess, because it's not that long, you'll see.